Yay! Welcome to the last lesson of your intro to limits. Today's lesson is limits and continuity. So when we're defining continuity for a function, we're looking at a particular point. And in terms of calculus, we have three different conditions, which really are the definition of continuity that we want to use. So in order for a particular function to be continuous at a point, x equals c, where c is some constant, the first part of our definition states that f of c is defined, meaning it is an actual point on the function. When x equals 7, then I get a point 7.2, for example. Okay, no open circles, no holes. The next part of our definition is that the limit as x approaches c, that constant value that you chose, of f of x exists. Again, remember, for the limit to exist, it has to have the left and right hand limits equal each other. And then finally, to prove continuity or to completely define our continuity, it states that the limit as x approaches c of f of x equals f of c. So where the function is defined, that value is equal to the limit as x approaches that value. There you go. All right, let's check through some examples and see how it works. So in our table, we have various c values for the given graph at the right. We're going to evaluate each of the function at each of those values, look at left and right hand limits, the overall limit, and then based upon what is f of c, what is the limit as x approaches c, is the function continuous, yes or no? So our first example is x equaling -5. So f of -5 is the ordered pair 5, -2, so that y value is -2. As we come from the left-hand limit is -2. The right-hand limit, however, is at 7. So does the limit as x approaches -5 exist? Nope, it sure does not. Therefore, since the limit doesn't exist, then that means the function will not be continuous at that particular value. Cool, now we got the first one down pat. Let's try to see if we can get through the others a little bit faster. Look at x equaling -3. So f of -3, the function is evaluated at -3 at -6. The limit from the left-hand side of -3 is 5. From the right-hand side of -3 is also 5. The limit as x approaches -3 equals 5. Is the function continuous at that value? It is not, and that's because f of c does not equal the limit as x approaches that c value, -3. All right, at 0, so x equaling 0, that is f of 0 is 6. The limit as x approaches 0 from the left is 6. The limit as x approaches 6 from the right is also 6, as x approaches 0. Therefore, the limit at 0 is 6. Is the function continuous at x equaling 0? Yep, it sure is. You got it. The function equals 6 at 0, and its limit is also equals 6. All right, here are 3 more examples. Same graph that we have, but evaluate your function at 3, 4, and 9. Find the limits at x equaling 3, 4, and 9, and determine if the function is continuous. So you guys, pause the video if you're watching, try these on your own, and then we'll scroll through. All right, here we go. F of 3 is 9. The limit from the left is 9. The limit from the right does not exist. The limit from, or overall, at x equaling 3 does not exist. Therefore, the function is not continuous. F of 4 does not exist because that is a vertical asymptote. The limit as x approaches 4 from the left approaches positive infinity, but we say doesn't exist. From the right, it approaches positive infinity, and then overall it does not exist. Therefore, the function is not continuous at x equaling 4. And finally, at x equaling 9, it is evaluated at 3.5. The limit from left of x approaching 9 is 3.5. From the right doesn't exist. We don't have any other points to the right of that point. Therefore, the limit doesn't exist, so the function's not continuous at 9. Great job with those. Let's continue on. Right, so remember, limits tell us the y value where the function is going towards, what value it approaches. However, our continuity guarantees that the function actually gets to that value and equals that y value. So we are now going to classify different types of continuities. We have removables or points, which we classify as a whole, and we see these in our two-sided limits. So there's two diagrams where you have a hole in the function. The graph works up until x equaling 1, or the other one also at x equaling 1. There's a gaping hole in that function. The limits exist, but the function does not exist at that point. We also have non-removable discontinuities. You will see a jump in the function in a one-sided limit. So it's approaching 1 at some value, and then it picks up and jumps to a different y value, same x. Okay, and you see that in two different examples for these graphs. And then the next non-removable discontinuity is an infinite discontinuity. So we're going to have at least one of the one-sided limits not existing. And these are going to occur when you're going to have a vertical asymptote, as seen in both of those examples. All right, example 2, check out the graph that we have. And we want to determine the interval or intervals at which the function is continuous and discontinuous. And we're looking, for this particular example, between -5 and +10, not including. So -5 less than x, less than 10. So we're looking at all the points where the function is continuous and not continuous. All right, so continuity means no holes, no asymptotes, no removable or non-removable discontinuities. So our function's continuous from -5 to -3, -3 to 3, 3 to 5, 5 to 7, where 7 is included, and then again from 7 to 10. Okay, meaning any place where you have an open circle, a hole, removable discontinuity, or a vertical asymptote in this case, or a jump in your function, you're going to have points of discontinuity. So we have at x equaling -3, that's a hole. It's a removable discontinuity. At x equaling +3, that's a vertical asymptote, which is a non-removable. And then at x equaling 5, that is another hole or point of discontinuity. And at x equaling 7, we have a jump where you see the function has a closed circle to an open circle. So it does also have that removable hole, point of discontinuity, but we consider that the jump, it kind of overrides at x equaling 7. All right, examples 3 and 4. Use what you know about rational functions to determine the intervals where the function is discontinuous, and then describe the type of discontinuity as infinite or removable. Again, we're looking at those x values. So example 3, we have f of x equals 1 over x minus 4. Okay, what kind of function is it? That's right, I see a big ugly fraction, so it's a rational function. And what do we know about rational functions? They have vertical asymptotes and horizontal or slant asymptotes. In this particular example, we have a vertical asymptote. Set that denominator equal to 0 to get x equaling 4. So that would be my vertical asymptote. If you substitute a 4 into the denominator, it makes the entire function undefined. Okay, so remember, in order for the function to be continuous, I have to evaluate it and get a point that's part of the function. In this case, at x equaling 4, it's undefined. And then again, x equaling 4 is the vertical asymptote. So that's a sketch, rough sketch of, thank you Desmos, what the graph would look like. So as we look now at the left and right side limits to prove that the limit does or does not exist, that's our second part of proving continuity. So the limit as x approaches 4 from the left, that is undefined. So to get a value, you would want to substitute in 3.9, 3.99, 3.999 in that denominator, so you could see that the numbers are getting smaller and smaller, going closer to negative infinity, as you see in the graph. The limit as x approaches 4 from the right, gives you the same thing, 1 over 0, which is undefined, and again, we would choose like 4.0001 and 4.001 and so forth to figure that the values from the right are approaching positive infinity. Therefore, as I look at left and right side limits, the limit as x approaches 4 of this function does not exist. Okay, so is the function continuous? Nope, it definitely is not. X equaling 4 is a vertical asymptote. We knew that from the type of function we recognized at the beginning, and we state that as a non-removable discontinuity, and in this case it's infinite because it's our vertical asymptote. All right, couple more, gang. Here we go. Number 4, doing the same thing. Our function is g of x equals x squared plus 6x plus 8 over x plus 2. Again, another rational function. So in this case, we're going to want to take a moment and factor it to see if the denominator is going to be, in fact, a vertical asymptote or if it would be a whole. Okay, so you can evaluate g of 2 as well and see what that value gives you. In factored form, we have the quantities of x plus 2 and x plus 4 in the numerator, x plus 2 in the denominator. So we see that our function is just left with x plus 4. So at x plus 2 as our factor, that gives us a whole at x equaling negative 2. All right, when we evaluate at negative 2, again, we notice that the function is undefined. And at the point negative 2, positive 2 is a whole. We classified that a moment ago when we looked at the factors. Now we're going to check left and right side limits. So again, we're approaching negative 2. That's our x value where it's undefined. So we want to see if the left and right sides both approach that whole. And again, we would substitute in values really close to negative 2, so negative 2.00001 and coming from the left, and negative 1.999 coming from the right to evaluate these limits. And we see that both of them are going to approach 2, which we determined was the actual whole. So the limit as x approaches negative 2 of g of x does exist. It equals 2. However, when we evaluate the function, it's undefined. So again, this function g of x as x approaches negative 2, its limit does not equal the function evaluated at negative 2. Therefore, the function is not continuous, and it again is a whole, a removable discontinuity. All right, we got just a few more and then we're done. Some piecewise functions. So number 5, h of x has 3 different parts to this function. Negative 2x minus 5 when x is less than negative 2, 6 when x equals negative 2, and x cubed minus 6x plus 3 when x is greater than negative 2. By all means, gang, type this in Desmos, rough sketch it yourself, and figure out what the graph is going to look like to help you. You can also evaluate it algebraically, looking at the table in your function, or just popping in x values and evaluating on your own. So h of negative 2 equals 6. That is the middle piece of this piecewise function. Okay, when we evaluate, that's exactly what we go to. Now check our left and right side limits. The left side limit, the limit as x approaches negative 2 from the left, we have to substitute a negative 2 in the first part of the function because that's where x is less than negative 2. It gives us a y value of negative 1. From the right, the limit as x approaches negative 2 from the right, use the bottom part of the function, x cubed minus 6x plus 3, substitute in a negative 2 for x, and you get a y value of 7. Left and right limits are not equal. Therefore, the limit does not exist as x approaches negative 2. Continuity fails. Definitely, it's out. H of negative 2 is a point, negative 2, 6. However, the limit does not exist. So this function is not continuous at x equaling negative 2. Alrighty, number 6, another piecewise function. We've got several questions for this one. Given j of x is 2x plus 1 when x is less than 3, and x squared when x is greater than or equal to 3. Determine the left, right, and overall limit as x approaches 3. Evaluate j of 3. Determine if j of x is continuous at x equaling 3, and then justify your answer. Okay, take a moment and try this and see how you do. Press pause, come back in a minute. All right, part A. The limit as x approaches 3 from the left goes into the top part of the function, giving you 7. The limit as x approaches 3 from the right goes into the bottom part of the function, which equals 9. Therefore, the limit as x approaches 3 of j of x does not exist because left and right side limits are not equal. When you evaluate the function j of 3, or at x equaling 3, again, use that bottom part. 3 squared gives us 9. So is our function continuous at x equaling 3? Definitely not. The limit as x approaches 3 does not equal the function evaluated at 3. I think you got this down pat, right? All right, so here's our summary. Summary of continuity. If a function is continuous at any given point, the function value, its y value, and limit value are equal at that particular point. So you've got to evaluate the function, check the limit, and see if those two things are the same. Great job with this lesson. Thanks for sticking through all of it with us for this intro to limits and the tail end of your pre-calc class. Have a great day, guys, and make sure that you do some practice and pop in if you have any questions whatsoever.